Module 4, Investigation 4, Partial and In-Unit Growth Factors. I'm really excited about this investigation. Number 1. Urban planners noticed that the population of a certain county doubled over 20 years from 1990 to 2010, following a pattern of exponential growth. The population of the county was 756,000 people at the end of 1990. What was the population of the country at the end of 2000? Let's just think about what we know for a second. In 1990, the population was 756,000. And we want to know what was the population in the year 2000. And the planners noticed that the population of the county doubled over 20 years. Oops, we don't want to know 2000, we want 2010. Okay, but we do know that it doubled, so the population in 2010 will be 756,000 times 2. Which is 1,512,000. Okay, part B, if the growth pattern were to continue for another 20 years, so another 20 years, that would be in 2030, what is the projected population? Well, if the pattern of growth were to continue, the growth is doubling every 20 years. So in another 20 years, we would expect it to double again. So 151200 times 2 would be 3,024,000 people. Part C, which quantities are changing in this situation? And which quantities are not changing? So changing, notice that the number of people is changing. The population of the county is a changing quantity. The time is changing. We went from 1990 to 2010 to 2030, so the time elapsed since 1990 is also changing. What's not changing? Let's see. The population in 1990, or at the end of 1990, that was fixed. That's 756,000. Anything else? The 20-year growth rate is not changing. We're always doubling. Okay. Part D. If we assume that this population will continue into the far future, complete the following table. Okay. Number of years since 1990. So in 0 years after 1990, that's in 1990, the population was 756,000. And then every year we double that. So the next year, there are 1,512,000 people. And if we continue to double this, we can fill in the rest of the table as follows. So far we've neglected to look at this rightmost column. The number of times larger the current population is than the population at the end of 1990. Well, in this first instance, we are in 1990, so the population is 1 times larger than the current population. Then here we're 2 times larger than the population in 1990. Here we double it again, so we're 2 times 2 or 4 times larger. Then we double it again, 2 times 2 times 2 is 8 times larger. Or after another 20 years we double again, so 2 times 2 times 2 times 2, 16. We can write each of these in exponential notation to help us with part E. This is 2 to the 4th. This one is 2 cubed. Here we have 2 squared. This is 2 to the 1st. This is 2 to the 0. You may remember that anytime you raise something to 0, you get 1. Part E. Define a function f that expresses the population of the county P after a number of 20-year periods. So I know my function P is going to be equal to f of my input after a number of periods n. And let's see, I noticed that I'm always taking my initial population, 756,000, and then I'm multiplying by 2 like a certain number of factors of 2 depending on how many years it is. Like this number here is 756 times 2. Then this one is 756,000 times 2 times another 2, with times the 2 squared here. So this is my function that will give me the population. There's probably something that we should note here. Notice that n is not the number of years. N is the number of 20-year periods. So if n equals 2, that corresponds to 40 years. So this formula wouldn't work if we wanted to find, say, the number of years or the population 10 years after 1990. Or maybe it would somehow. We'll get to that later. Number 2, since 20-year changes in time are quite long, we might want to know how much the population changes over shorter periods of time, say for instance 10 years. Given that the population grew exponentially, which of the following best describes what happens every 10 years? 1. Every 10 years the population increases by a constant amount. That is, a constant amount is added to the population at the end of 1990 to get the population at the end of 2000, and the same amount is added to get the population at the end of 2010. So is that what's going on, or is the situation more like part 2? Every 10 years the population increases by a constant factor. That is, this constant factor is multiplied by the population at the end of 1990 to get the population at the end of 2000. And this constant factor is multiplied by the population at the end of 2000 to get the population at the end of 2010. Well, let's consider number 1 for a second. Every 10 years the population increases by a constant amount. Did we see that with 20 years? Did we increase by the same amount here? Like you can check on your calculator. If we take 15120 0, 0 and subtract 756000, we see that's an increase by 756,000. We just doubled. But then the next 20-year interval we're going to double again, but it's the increase isn't 756,000. The increase is 1,512,000, which you could, again, subtract those, but that was kind of tedious. Notice each 20-year interval, the amount we're increasing has actually increased. Here, from the years 60 to 80, we increased by 6 million, roughly. So it's definitely not situation 1. We actually have situation 2 here. The population increases by a constant factor. In this case here, every 20 years we increased by a factor of 2. That's our growth factor here, our 20-year growth factor. Now we're also going to have a different 10-year growth factor. And so how are we going to figure that out? That's the question in part B. Given that the population increases exponentially and doubles over 20 years, what was the 10-year growth factor? Okay, this is a pretty tough question, but let's think about what we already know. We know that in 20 years, population doubles. Okay. Let us just call G the 10-year. Let G be the 10-year growth factor. So we know if we take our initial value, which is, so this is what we know. We know that if we took our initial value and multiplied it by 2, we'd get the population 20 years later. Now think about this for a second. 20 years is just 2 10-year intervals. So if we start with our initial population, if we multiply by the growth rate G, that'll tell us what the population is after 10 years. And if we multiply it again by another 10-year growth factor, that will tell us the population in 20 years. Okay, now let's divide both sides by 756,000. So we have G times G equals 2. That means that G must be the square root of 2. You could think G squared equals 2, take the square root of both sides, and you'll get G is the square root of 2. That's our 10-year growth factor. Now we can do something similar to find the 1-year growth factor. So let's let B be the 1-year growth factor. Just like G times G equaled 2, if we multiply B by itself 20 times, we're going to get 2. Another way that you can think about this is B multiplied by itself equal to 20. B multiplied by itself 20 times is the same as N. Taking the 1-year growth factor and multiplying it by itself 20 times is the same as the 20-year growth factor too. So this means that B to the 20th equals 2, and to solve for B, we take the 1/20th power of each side. B is 2 to the 1/20th, or the 20th root of 2. If we multiply the 20th root of 2 by itself 20 times, we'll get 2. You could have also used the fractional answers for these. The square root of 2 is about 1.14, and the 20th root of 2 is about 1.03526. So what is the 2-year growth factor? We know that the 1-year growth factor, B, is 2 to the 1/20th. And remember that the growth factors, they tell us the next output value if there's a in-unit increase. So for the 1-unit growth factor, if we multiply, say, some population by this number, it'll tell us the population the next year. So if we want 2 years, we just multiply that by itself 2 times, the 1-year growth factor twice, b squared, which is just 2 to the 1/20th squared. Now your properties of exponents say that you can multiply these here. 1/20th times 2 is 2/20th, or 1/10. 2 to the 1/10. And that's about 1.07177. The 7th year growth factor will just be b to the 7th. Which is 2 7/20ths is the exponent, which is about 1.27456. I forgot that we have to find the 3-year growth factor also. That'll just be b cubed, which will be 2 3/20, which is about 1.10957. Now we're supposed to complete the following table. Let's see, we have the number of years since 1990 and the population. So we had our initial population, 756,000. Remember our 1-year growth rate is 2 to the 1/20. So to find this next value, it's just 756,000 times our, since we're increasing by 1 year here, we just use our 1-unit growth rate, or growth factor. And let's see what we get. Sorry if I said growth rate a whole bunch of times. It's really the growth factor. Okay. 782660. We could, since now we have this value, we could multiply by 2 to the 1/20th again to get the next value. Because we're increasing by 1 year here, so we can use the 1-year growth factor. So I'm just going to take on my calculator, and I already have that number from 782660, multiply by 2 to the 1/20th, 810261. I can do the same thing again here, but I'm just going to demonstrate something different. Notice that here the number of years increases by 3, so I could use my 3-year growth factor, which, remember, that was 2 to the 3/20th. We could simply take the original population, 756,000, and multiply by the 3-year growth factor. Notice that we just have, it's really just this 1 year growth factor multiplied by itself 3 times. And that gives us 838, 835. So for this one, for the 13th, I could just take my original and multiply it. Either you could think about this 2 ways. I could use the 1 year growth factor and I'm just doing this 13 times, or you could use the 13 year growth factor, which is 213 over 20. Either one. But you should get 1,186,291. I'm going to go ahead and fill in the rest of the table. Okay, to find a function g that expresses the population of the country P as a function of the number of years t since 1990. So I want the population P, and my function name is g. The input is t, and t is the number of years. It's different from before where n was the 20-year increments. But this pattern here sort of tells us what to do. We take our initial value, 756,000. We can take our 1 year growth factor, which is 2 to the 1 over 20th, and then raise it to t. Equivalently, like that answer that I wrote is perfectly fine, or you may have written this one. It's really the same answer, just written in a different way. Part D, to find a function h that expresses the population of the county C months since the end of 1990. So I want my population to equal this function h of C. So I think again I'm going to have my initial population involved in the equation. But I need a growth factor of a 1 month growth factor. If 2 to the 1/20th is the 1 year growth factor, then what is the 1 month growth factor? Let's call it m. We know that if we take m and multiply it by itself 12 times, we should get the 1 year growth factor. That means that m is 2 to the 1/20th to the 1/12th. And we could do 20 times 12. That is 240. So this is 2, and the exponent is 1 over 140. That was an awesome problem. Hope there's more awesomeness in number 3. A farm in Canada had 218 alpacas on January 1st, 2004. Okay, so we start off with 218 alpacas. There's our initial value. After 8 years, the alpaca population decreased to 187. Assume the number of alpacas decays exponentially. What is the 8-year growth decay factor? So right away, I notice that we have 218 alpacas to start with, and then we decrease after 8 years, and we have 187 alpacas. And if we want the 8-year growth decay factor, it's really a decay factor. We just need to find the number that 218 multiply by that number. Let's call it D for decay factor. Gives us 187. And so D simply equal to 187 over 218. and that is about 0.858. So there is our 8-year decay factor. What is the 8-year percent change? Well, that's simply the decay factor minus 1. It's a percent decrease. Negative 0.142, which is negative 14.2%. So we're decreasing by 14.2% every year. I'm sorry, not every year, every 8 years. Part C, assuming the alpaca population continues to be modeled by the same exponential model, how many alpacas can we expect to be on the farm January 1st, 2020? So we started in 2004, and we went 8 years, and that would be 2012 when we got 187. And then if we went 8 more years, we'd be at 2020. And so we can simply take the time here in 2000, or the number of alpacas here, 187, multiply by our decay factor, 0.858, and that's our 8-year decay factor. That will tell us the number of alpacas 8 years later. And we have about 160 alpacas. You could have also taken the original population, 218, and multiplied by 0.858 twice, or 0.858 squared. Part D, since 8-year changes in time are quite long, we might want to know how the population of alpacas changes over shorter periods of time. What is the 1-year growth/decay factor? So essentially, we want to know what is the factor that if we multiply it by itself 8 times, 1, 2, 3, 4, 5, 6, 7, 8, we get our 8th year growth or decay factor, which is 0.858. So we know that the 1-year growth factor is an 8th power, and it's equal to 0.858, or 0.858 to the 1/8, the 8th root of 0.858. And that's about 0.981. So what is the 1-year percent change? It's simply the decay factor minus 1. That's 0.019, or negative 0.019. So negative 1.9%, or a decrease of 1.9% every year. It's kind of interesting to think about the 1-year percent change, 1.9% decrease every year, but over 8 years there's a 14.2% decrease. Part F, define a function f that relates the number of alpacas on the Canadian farm T years from January 1st, 2004. Assume the alpaca population continues to change by the same decay factor each year. So we know that our initial number of alpacas was 218. Our decay factor, our 1-year decay factor, is 0.981, and we raise that to t. Okay, so we have our exponent t. Had a little bit of technical difficulties there, but here's our function for part F. Number 4, assume the number of alpacas continues to change by the same decay factor each year as defined in exercise number 3. Use your calculator to determine the following. After how many years will there be 109 alpacas remaining on the farm, assuming the herd started with 218 alpacas? So think about what our function represents. This f of t gives us the number of alpacas here. So we're not having an input of anything of t here because we don't know what the t is. We're looking for t. We want to know what's the value of t that will give us 109. So 109 is the output. And we need to find t. Okay, it says use your calculator. So how would we use our calculator to do this? One way is if you go to y equals and say y1 is equal to 109, which represents the left-hand side of our equation, and y2 equals 218.981 t, the right-hand side of the equation, and if we graph those two functions and we find the intersection point, that's going to give us the value of t. So we'll have something like this. This will give us the value of t, where the output is 109. And you can press second, calculate, or trace, and then go to intersect and hit enter twice, and then press enter. I think just hit enter 3 times and it'll tell you the intersection point. You might have to change your window to make sure that you can see the intersection point. Like the y max will have to be at least like 110 or something, and you have to make your x max at least 40 because the intersection point is 36. After 36 years, the number of alpacas will be 109, and you can check that by plugging 218.981 36 and you'll get 109. So after how many years will there be 55 alpacas? You could do that the same way. And if you do, you'll find that it's 71.8 years or so. After how many years will a herd of 120 alpacas decrease to 60 alpacas? So basically we can solve this equation. 120 equals 218 times 0.8981. I'll call this T1 because it's our first time. And find out what T1 equals. And we can use our calculator and do that the same way we did the last two. And then we could do the same for 60. And get T2. And then if we subtract T2 minus T1, we'll get our answer. Another way to do it, since we know the 1-year growth rate or growth factor is 0.981, we want our final value of alpacas to be 60, and our initial we could consider it 120, and we could solve that for t using the calculator. Whichever way we do it, you'll find that the solution is 36. So notice that that's the time it took the population of alpacas to decrease by 60, or to be cut in half. Notice that this answer 36 is the same as the one we got above for part A, because again there was a decrease by half. Anytime we're finding how long it would be for the population to decrease by half, it's going to be the same number of years. That's called the half-life. Number 5, assume the number of alpacas continues to change by the same decay factor each year as defined in problem number 3. Okay, so in problem number 3, that decay factor, I think it was 0.981. Yeah, that was our 1-year decay factor. Just going to make a note of that. Because now we want to know what is the 1-month decay factor. So there are 12 months in a year, so if we call the 1-month decay factor m, we know that m times m times m to the 12th is going to be the same as the 1-year decay factor. So m is the 12th root of 0.981, or 0.981 to the 1/12. And that is 0.998. So this essentially means if we take our initial value, number of llamas, or take any number of llamas, and multiply it by 0.998, it'll tell us the population of llamas 1 month later. Or if we multiply by 0.998 12 times, it'll tell us 1 year later, which is the same as just multiplying by 0.981 once. Define a function g that relates the number of alpacas on the Canadian farm k months from January 1st, 2004. So g of k will equal the initial number of alpacas, which I think was 218. And then our decay factor is 0.998, and the number of months is k. Recall this is just the general exponential form with our initial value and our decay factor and the input, in this case number of months. And we have our decay factor, 0.998, is in terms of the number of months. What is the 2-month growth decay factor? The 2-month growth decay factor will just be the 1-month growth decay factor multiplied by itself, or 0.998 squared. Which is about 0.996. There's our 2-month decay factor. Number 6. After taking medicine, your body begins to break it down and remove it according to a pattern of exponential decay. Suppose you take 500 milligrams of ibuprofen and your body removes 85% of the ibuprofen every 5 hours. Define a function f that expresses the amount of ibuprofen b present after n 5-hour time intervals since taking the medicine. So I know I want my function to give me the amount of ibuprofen b, and it's f, and the input is n, the number of 5-hour time intervals. And I know that since there is exponential decay, this is an exponential function. I'm going to start with my initial amount, 500 milligrams, so that tells us the output of this function will be in milligrams also. And I just need my decay factor here. And this is actually going to be the 5-hour decay factor is what I need, since my units of the input are 5-hour intervals. So how do I find the 5-hour decay factor? Well, we know that the body removes 85% of the ibuprofen every 5 hours. That's the percent change, though. Each hour we're going to remove 85%. So that means that the decay factor is 0.15, because the decay factor is always 1 plus the percent change, but the percent change is a decrease, negative 0.85. So if we take our original amount and multiply it by 0.15, if we just do that one time, it'll tell us that the amount 1 hour later. Notice that that'll be 15% of what we started with, because 85% will have been removed. Then after another hour, another 85% will be removed, so we multiply by 0.15 again to get the new amount. Part B, define a function g that expresses the amount of ibuprofen B present t hours after taking the medicine. So here we want our function to be in terms of hours. Instead of 5-hour intervals, we want the input to be hours. And so since we have the 5-hour decay factor, and we know that the 1-hour decay factor, which is n, we know that the 1-hour decay factor is just, we just multiply it by itself 5 times to get n. So let's call the 1-hour decay factor little b. We know b to the 5th will equal n, or b equals n to the 1/5, and n was 0.15. So a 5th root of n gives us the 1-hour decay factor, and this is about 0.684. So there's our decay factor, which goes right here in our function. I realize that I can't barely see this cursor on the screen, so sometimes I'll be looking for it and it probably looks crazy from your end. Part C, how much ibuprofen remains in your body 3 hours after taking the medicine? So now we have this nifty little function. 3 hours after taking the medicine, that means the input is 3. We can simply type this into the calculator to get the number of milligrams in our system 3 hours later. And that's about 160 milligrams. To find the amount after 12 hours, it's the same process. Something like 5.24, somewhere around 5.2 milligrams. Part D, how does the change in the amount of ibuprofen remaining change as the number of hours elapsed increases? So basically, as we have changes in time, how does the amount of ibuprofen change? So what happens to this? So the short answer is the changes are decreasing. Notice that we started off with 500. After 3 hours we dropped to 160. That was a huge decrease. But then after 9 hours we dropped from 160 down to 5.2. The decreases are getting smaller.